So, in my last lecture I discussed the single objective or mono objective optimization problem for solving this power distribution system planning. Okay. And in this lecture I will talk about this multi objective optimization problem, In fact, our objective functions etcetera would be same as that of the previous planning problem, but if you can remember my last lecture, you have seen that we had two objective functions formulated. One is the objective function related to the cost, another is the objective function related to reliability. Okay. And we formulated two planning problems, two optimization problems. In one problem, we solved a planning problem where our objective function is minimization of total cost. In another problem, we solved a planning problem where our objective function was the minimization of total interruption cost, and thereby we will try to maximize the reliability of the network. Okay. Now, in general, this cost and reliability, these two objectives conflict with each other. In fact, I discussed this in the third module when I was talking about this reliability assessment, that this cost and reliability, these are conflicting objectives which conflict with each other. What does it mean? It means that when we have this cost optimization, we will never get a solution which would be most reliable. Similarly, when we will do optimize this reliability, we will not get a solution which will be that the best solution or best economical solution or best solution in view of the total cost. So, there exists conflictness. I will talk about this in fact after a few while. Okay. In fact, when we have this type of optimization problem, we call this as multi objective optimization problem, where we have multiple objective functions which conflict with each other. And here we have the same objective functions as we have formulated in my last lecture. One is total cost, another is total interruption cost. Total cost refers to the total investment and operational cost, and total interruption cost is basically the cost associated with all sort of faults or interruptions. Okay. And when we have this kind of conflicting objectives, we use this multi objective optimization approach. It is a very big domain in optimization theory. I will not go into detail of that, but I will give you some insight to understand that what is multi objective optimization problem and why we need to have a special care for solving those kind of multi objective optimization problem. Okay. Now, in multi objective optimization problem, unlike the single objective or mono objective optimization problem, there exist a number of solutions instead of a single optimal solution, and this number of solutions we are called this trade off solution, or they are known with a special nomenclature that is called non dominated solution. I will come to that. Okay. So, in multi objective optimization, our goal is to have simultaneous optimization of multiple objective functions which conflict with each other. Okay. Now, I will give an example here. Suppose I have a optimization problem where I have two objective functions. So, optimization problem with two objective functions. Okay. It is very simple example to understand the usefulness of multi-objective optimization approach. So, in one optimization in this optimization problem, the one objective is f 1 x. It is a single variable optimization problem, where objective function is f 1 x is equal to x square. See, this is objective function 1. Okay. And another objective function is f 2 x is equal to x minus 5 square, let us say, okay, or x minus 10 square or x minus 2 square or whatever you can call. Okay. So, let us consider it is as x minus 2 square instead of x minus 5 square. So, this one is our objective function 2. Objective function 2. So, this is a case of unconstrained single variable optimization problem. So, this is unconstrained single variable optimization problem with two objective functions. With two objective functions. Okay. And let us consider that our goal is to minimize both the objective functions. Our goal is to minimize both the objective functions. Now, since this problem is of a single variable, we can easily sketch the function f 1 x and f 2 x with respect to this variable x. Okay. So, let us do that. So, this is x starting from 0 to infinity, and this in this direction, this is negative. Now, this one is suppose f 1 x. So, if we plot this f 1 x with respect to x, how would be this plot? This plot would be something like this. Okay. So, this one is our f 1 x. Okay. Now, I am also plotting here this f 2 x, then how would be this plot? Suppose this is x is equal to 2. So, this plot of this f 2 x would be something like this. So, this is f 2 x. So, this is f 1 x and this is f 2 x. In the same graph, I am plotting both the functions, one is f 1 x, another is f 2 x. Okay. And as you have seen that our goal is here to simultaneously optimize both the objective functions, Okay. So, here our goal is to simultaneously optimize both the objective function. Okay. Now, I will create three regions for these values of your x. One is this region, one is this, another is this. So, here this is basically when x is lower than 0, and this is the zone where x is greater than 2, and this is of course, this is when x vary between 0 to 2. Okay. Now, looking at this characteristics or looking at this graph, one can understand that at this region when x is equal to 0, both f 1 x and f 2 x are in decreasing trend. If we increase this value of x. Okay. So, if x increases and both variations are in decreasing trend. Okay. So, here when x is equal to 2, both f 1 x and f 2 x are in increasing trend. Okay. So, you can see from beyond this x is equal to 2, both are increasing. Okay. Now, what will happen when x is equal to x is in between 0 and 2? Okay, if you look at in between this f 1 x is in increasing with the increase of x, and f 2 x it is decreasing with increase in x. Okay. So, in this region, now if we consider that if we optimize this both the objectives at this region when x is equal to x lower than 0, since both the objective functions are in decreasing trend or with the same type, they follow the similar characteristics, we can easily find out that what would be the solution if we optimize both the objectives together, and that will eventually similar to an objective function, that f x is equal to f 1 x plus f 2 x. That means, if you simply aggregate these two objective functions and if we minimize that, then whatever solutions you are getting, that will be the solution of that particular problem. Similarly, same thing is applicable when x is greater than 2. You simply aggregate f x is equal to f 1 x plus f 2 x, and if you optimize that function f x, then whatever solution you will be getting, that will be the optimal solution beyond this x greater than 2. But in this region when x is in between 0 and 2, since both the objectives are in opposite trend, one is increasing with respect to this variable, another is decreasing with respect to that variable, then we cannot simply aggregate two objective functions, and we can tell that whatever solutions we are getting, that is the optimal solution, that we can't. Why we can't? Because both are basically in opposite trend and or both will conflict with each other. For example, here you can see at x is equal to 0, that f 1 x is value is 0, but f 2 x if you consider this region, f 2 x is of highest value, f 2 x is of highest value. Okay. So, although f 1 x is of lowest value, but f 2 x is a highest value. Okay. So, if we independently analyze these two objective functions, then it may appear to me that f 1 x is getting optimized, that function 1 is getting optimized, but the function 2 is not. So, when function 1 is giving you the best solution for its own function evaluation, the other function, that f 2 x is having the worst solution. Okay. Now, same thing is applicable when x is equal to 2, that f 2 x is providing the f 2 x, that the second function is having the lowest value, whereas f 1 x is having the highest value. Okay. So, here you can see this is highest value, highest value of this your f 2 x and lowest value of f 1 x. And here you can see that highest value of f 1 x and lowest value of f 2 x. Okay. And in between all these points, all these values of x, all these values of x, you can see there are certain points where we have your f 1 x is decreasing, but f 2 x is in fact, there are certain points you can see that f 1 x is having higher value and there are certain points f 2 x is of higher value. Okay. And we cannot simply aggregate these two objectives. If we do so, then we cannot independently find out that which one is having the best solution. In fact, if you aggregate these two, then it may so appear to you that this is probably the optimal solution, but this is optimal solution in view of the aggregation of both the objectives, but not in view of the individual objectives. If you have the individual goals that I need to optimize both f 1 x and f 2 x, then that solution will not provide you the optimal solution either in the objectives. Okay. And that is why we cannot simply aggregate these two functions to have a we cannot make aggregation of these two objective functions to form a single objective. So, we cannot do so, because both the objectives behave differently, and that is why we call them conflicting in nature. So, if suppose f 1 x is your objective function related to the cost, then you get the best solution at x is equal to 0, but at that if f 2 x is your objective function related to the reliability, then at this particular solution that f 2 x is the worst. So, that means, when cost is the in view of this objective function related to the cost, if it provides the best solution, in view of the reliability it provides you the worst solution. Okay. And suppose if you do not have any preference prior to this optimization, that I would prefer one particular objectives over other, then you cannot decide that which one should be the best solution among these two, and that is what this goal of having this multi objective optimization. In multi objective optimization, suppose if we have this type of conflicting objectives, we do not arrive at a single solution, rather we say that each and every point might be one solution for this one prospective solution for this optimization problem. And if we plot these solutions in the objective function domain by keeping this f 1 x and f 2 x in two axes of this plot, then you will get different solutions which will be something like this, In fact, all points of x will have a feasible solution. So, basically this plot would be a continuous plot like this, where each and every points will represent a prospective solution. So, this type of plot is called in multi objective optimization, this type of plot is called non dominated solution. And a set of optimal non dominated solution is called this final solution of a multi objective optimization approach. Okay. Now, so one needs to understand one thing, that this will work when we have two objective functions and both the objective functions will conflict with each other, meaning that in one case when you are getting the best solution, in view of the other objective functions, you are getting it as a worst solution. So, this is probably the best solution in view of this f 1 x, but worst solution in view of f 2 x, because it is having the highest value, and vice versa. Similarly, these two corner solutions of this will give you the two solutions where you get one objective functions best value, another objective functions worst value. Okay. So, this is what the goal of this having multi objective optimization problem, instead of aggregating these objectives together like this, because it is not possible to have an aggregated objectives when we have two objective functions which are of different trend, which behaves differently, which conflict with each other. Okay. And we have different approaches for multi objective optimization, for solving multi objective optimization problem. So, let me write solutions or rather solution approaches for multi objective optimization problem. So, there are different types of solution approaches proposed time to time for this solving multi objective optimization problem, and it is a very well known paradigm of research in optimization theory, and many people across the globe are working on this. Okay. So, there are some broad categorization possible on depending upon the different types of multi objective optimization approaches. One is called at weighted aggregation method. Weighted aggregation approach. This is one of the approaches. I will talk about this. Another approach is called Pareto-based approach. Okay. What is this? I will also come. Another is epsilon constant approach, or I should write it in words, epsilon constant approach. Okay. Or and there are other approaches as well, for example, lexicographic approaches. I am not going into detail. So, there are different approaches for solving this multi objective optimization problem. So, one needs to go through the literature of multi objective optimization problems and multi objective optimization algorithm or solution strategies for multi objective optimization problem, in order to understand that what are the different types of approaches already reported in the literature for solving this multi objective optimization problem. Okay. Now, what do you mean by this weighted aggregation approach? In this approach, although we cannot aggregate these multiple objectives which conflict with each other, but here in weighted aggregation approach, it is similar to a single objective optimization approach, where multiple objectives are weighted and aggregated. So, suppose I have a two objective optimization problem, where our objective function is objective functions are f 1 x and f 2 x, and we simultaneously minimize that these two objectives. So, here what we do here, we aggregate both the objectives with some weights. So, where W 1 and W 2 are weights. Now, if you do so, then obviously you will get a one solution for this particular by solving this particular problem. Now, here as I told you, one solution will definitely not represent that the optimal solution when we have multiple objective functions which conflict with each other. Okay? And that is why what they do different combinations of weight in order to get different solution and then plot this. So, this W 1 and W 2 are taken as the values of this W 1 and W 2 are taken as different combination of weights. So, different combination of W 1 and W 2 is taken to find multiple solutions. Okay. So, in this approach we need to run this optimization algorithm multiple times in order to have a multiple solution by assigning different combination of these values of the weights. Okay. Now, this is weighted aggregation approach, but there are some merits demerits which you need to learn by going through the literature of multi objective optimization theory. Now, there is another approach that is called Pareto based approach, which I have used for solving this multi objective distribution system planning problem. I will come to that. And there is another approach which is called epsilon constant approach, in which even though we have multiple objective functions, we convert. Suppose we have this f 1 x to f m x, we have m number of objective functions for a particular problem. In epsilon constant method, we optimize only one objective function. Let us say this is a minimization problem. We keep only one objective function, and the rest of the objective functions are converted to some constant. So, f 2 x we convert to some constant. So, let us write it as f I x to constant, where this constant is made with this value of epsilon. So, epsilon I represent the constant for this ith objective function, and this value of epsilon I is suitably chosen. So, that we get a multiple solution by varying different values of this epsilon. So, this is what this epsilon constant approach. We will not be discussing this here. One needs to go through the literature of multi objective optimization to understand this in a broader way. So, here we will be using this Pareto based approach. In the next slide, we will be shown you this Pareto based multi objective optimization approach. Now, this approach, why it is called Pareto based approach? Because this approach is proposed by Professor Pareto, who was a French economist and Italian born French economist, who proposed this Pareto based approach for multi objective optimization problem. Now, again we go back to this this main problem, so that I can let you know this what is our optimization problem all about. So, if you can go back, you can see so we had two objective functions formulated. One is called this total installation operational cost, that is CIO, another is total interruption cost, that is CIN. And when I solve this problem with a as a single objective optimization problem, we considered both the objectives at a time and we formulated two optimization problems. One is problem 1, another is problem 2. Now, here the advantage of this multi-objective optimization approach is that we will simultaneously consider both the objectives and we can solve the problem as a whole. So, here our goal is to simultaneously optimize both the objectives. So, here our goal is to simultaneously minimize CIO and CIN, and of course, these two are two different objective functions. One is related to total cost, which includes that total investment and operational cost. Another is related to total interruption cost, which is related to reliability. By minimizing what we can get a solution which would be a reliable solution. Okay. And this both the objectives we simultaneously optimized under the constraints of we have equality and inequality constants. We have equality and inequality constant, equality and inequality constants, which already I discussed in that lecture where I discussed this problem formulation. In equality constants is to balance the power of all these distribution nodes. So, this is power balance constant, and inequality constants are the capacity constants. Capacity constants for individual substation, individual feeders, individual ampacity constant of this feeder branch, and also this voltage limit constant. So, capacity constant and voltage limit constant. So, these are the constants we have in this problem. So, here our goal is very clear that we need to simultaneously optimize these two objectives under this various equality and inequality constants. Okay. So, in previous example I have shown you that we optimize one objective at a time and thereby creating two different problems, but here we are merging these two different problems in a single problem by not aggregating this objective function, but by considering the simultaneous optimization of both the objective functions. Okay. Now, this is what I discussed. This multi-objective planning is all about simultaneous optimization of objective functions by using this Pareto dominance principle. Again, what is Pareto dominance principle? I am coming to that. Then we have solved by using a multi-objective optimization approach, which is called as strength Pareto evolutionary algorithm 2 SPA2 to solve this multi-objective optimization problem for distribution system planning. And this SPA2 is initially a problem which is proposed in genetic algorithm, and we have extended this to this particle swarm optimization approach. And so, we call this whole approach as strength Pareto evolutionary algorithm 2 SPA2 based multi-objective particle swarm optimization. Okay. So, we call this often as SPEA2 MOPSO, which stands for strength Pareto evolutionary algorithm 2 based multi-objective particle swarm optimization. Okay. So, we use for both static and expansion planning problem, that is for 21 node data as well as 100 node data. Now, what is Pareto dominance principle? So, it is something that one needs to understand very clearly. Now, in Pareto dominance principle, we call that a solution dominates another solution if it is strictly better in view of one objectives, and in view of the other objective it is equally good or it is not worst as compared to the other solution. Suppose I have two objective functions, one is f 1 x, another is f 2 x, and I have two solutions, one is capital X, another is capital Y, okay, and also one is capital Z. So, x, y, z are three feasible solution. Feasible solutions. Okay. So, now in this Pareto dominance principle, according to this domination principle which is mentioned over here. So, we call a solution x dominates a solution y if it is strictly better. This is suppose minimization problem. So, this condition means it is strictly better, strictly better in view of jth objective functions, objective function, okay. And it is equally good means it is not worse in view of other objective function as mentioned over this condition. So, if both the conditions will satisfy, then we call the solution x will dominate solution y. So, in order to visualize this, let us have three possible solution or three candidate solution or three feasible solutions which represent with these dots. Okay. Now, as you can see for the solution x, this is the value of this in view of this objective function 1, and this is the value of this objective function 2. This is the value of objective function 2 and this is the value of objective function 1. Similarly, for this solution y, this is the value of objective function 2 and this is the value of objective function 1. And for this solution z, this is the value of objective function 1 and this is the value of objective function 2. Now, we compare these solutions one by one. Okay. So, you can see this if you compare the solution x and solution y, then you can see since our goal is minimization problem, it is a minimization problem and our goal is to simultaneously minimize both f 1 x and f 2 x. Okay. Now, if so, then in view of this both the objectives, you can see x solution x is providing strictly better solution than solution y. So, x is strictly better because in view of both the objective functions, you can see solution x is having lower values of this objective function, okay, in view of both the objectives. Now, that is why we call that x, the solution x dominates solution y, solution y, solution y. So, we call that x dominates y because in view of both the objective function, in view of the values of both the objective function, x shows the better solution, s shows strictly better solution, okay, because it is having lower value of the solution in view of objective function 1 as well as objective function 2. Okay. But if you compare this solution x with solution z, then you can see that in view of this objective function 1, in view of the objective function 1, because it is a minimization problem, this solution z is having better solution, but in view of objective function 2, the solution x is having better solution. So, when we have that type of condition that one solution is better in view of one objective and other solution is better in view of other objective, then we cannot call that either x dominates z or z dominates x. So, in that case we call x and z are non-dominated solution, non-dominated or non-dominated solution. Okay. So, what we call non-dominated solution? When we have two solutions in which none of them is strictly better than other, keeping the other objective function values not worst. So, here you can see x is having this strictly better in z in view of one objective, but the solution z is also strictly better than x in view of other objective. So, when this type of condition will exist, then we call both the solution are not dominated each other, rather they are non-dominated solution. Okay. And a set of non-dominated solution constitute a Pareto front, and a set of optimal non-dominated solution called as Pareto optimal solution. A set of optimal non-dominated solutions is called Pareto optimal solutions. Okay. A set of optimal non-dominated solution is called Pareto optimal solution. Okay. And in multi-objective optimization approach, our goal is to obtain this Pareto optimal solution, that one needs to understand. Okay. So, this is the pseudo code of SPA2 based multi-objective particle sum optimization for solving this distribution system planning problem. So, here again we initialize this population size of this PSO, we also initialize this maximum iteration that should be executed or beyond which this program will be terminated, and we update this velocity and position of this particle according to this PSO principle that already we have mentioned, but here since we have two different objective functions. So, we have two different fitness functions for this particle, and you have seen that we update this velocity and position of the particle in view of the fitness function. Now, here we have two fitness functions, okay, and that is why it is multi-objective optimization problem. And by using the principle of strength Pareto, we convert this two fitness function into a common fitness function, okay, and then accordingly we rank the solution, accordingly we find out this non-dominated solution and so and so. Okay. So, by using this Pareto dominance principle, we find this non-dominated solution, and by using this strength Pareto evolutionary approach, we assign this fitness function to individual particles, and thereby we solving this problem similar to the previous single objective optimization problem. Now, these are the results. These are the results that we got for different systems. So, this A represents this that solutions of 21 node system, B is representing this solution for 54 node system, C is representing the solution for 54 node system, and D is representing the solution for 182 node system. Okay. So, what you can see that each of this black dot, they represent one candidate solution, and we get a set of solution, okay, a set of non-dominated solution, but we cannot call them as a set of optimal non-dominated solution, because that you already have discussed that in particle sum optimization we cannot comment on this optimality of the solution. We cannot say that whatever we are getting at the end, that is the optimal solution. So, that is why this set of solution is not Pareto optimal solution, rather they are Pareto approximation solution. Okay, Pareto approximation solution, which might be closer to the Pareto optimal solution, and we have done several statistical analysis in order to find this how they are different from one approach to other. Okay. So, another thing you can see that this nature of this plot of this Pareto approximation solution, which is called Pareto approximation front, and this Pareto approximation front depends on the different types of problems. So, it is a very much problem specific. So, here its shape is different than this shape for the other problem, which is of different planning problem, which is of 54 node system. Similarly, here you get a different shape and here you get a completely different shape. So, the plot of this Pareto approximation solution, which is also called Pareto approximation front, will show you that how different the different problems are. Also, one thing you can see that two corner solutions are marked here. One is this and this for this Pareto front, one is this and this for this Pareto front, and one is this and this for this Pareto front. Okay. So, in view of this one objective, that is total interruption cost, this solution is having the lowest value, but it is having the highest value in view of the other objective function, and that is why this solution is called as most reliable solution among this Pareto approximation solution, because it gives the best solution in view of this total interruption cost, but worst solution in view of the total investment and operational cost. So, these two corner solutions are the two best solution in view of one objective each. Okay. So, one solution is the best solution in view of cost objective, another solution is the best solution in view of reliability objective, that one needs to notice. And here also we have a performance comparison with this paper, and this is the source of this our data for this 21 node system and 100 node system. And we got that in fact, we compared these two corner solutions only, and we got this for this proposed approach, that is SPA2 based MOPSO. We have the better solution in view of this economical objective, and in view of this reliability objective, it is slightly higher values for this corner solution, and therefore, we cannot comment that in view of both the both solution, this we are getting the best solution, but we can say we are getting competitive solution for this approach. Okay. So, let us have a summary over here. So, here up to this we completed this discussion of mono and multi objective distribution system planning problems and corresponding solution strategies. We call them as multi objective optimization solution. These are discussed for different types of planning problem, which include static problem or expansion problem. Also different types of encoding decoding scheme we have used, and the performance assessment of several statistical tests already we have shown in mono objective problem. In multi objective problem is not shown over here, but one can go through the paper where we publish this result. I will show you at the end in the reference list. Now, I will talk about another approach for multi objective optimization for solving this multi objective optimization problem, that is called dynamic planning, or sorry, that is called dynamic programming. Okay. So, dynamic programming or DP, it is a very well known solution strategy. It is a kind of enumerative strategy. It is not a meta heuristic approach, which gives different solution after different execution of simulation, but it provides same solution at the end of this execution, and it is a kind of enumerative approach. It works with certain logic. Okay. And our goal was to have a qualitative and competitive performance comparison of this dynamic programming with this multi objective particle sum optimization algorithm. Okay. Now, why we have chosen dynamic programming? Because it it is not a solution strategy which is very problem specific, unlike linear programming, and so rather it can work with any type of problem, whether the problem is non-linear or whether the problem is non-differentiable. So, linearity does not the requirement for application for this particular approach, and we can also extend this approach for solving multi objective optimization, which we have done, and we publish this one also in a reputed journal. I will talk about in the reference list. Also we provide some comparison. Okay. Now, what is dynamic programming? So, basic philosophy of this dynamic programming is its key ingredients are optimal substructure and overlapping sub problems. Okay. Now, what do you mean by overlapping sub problem? An illustrative example is shown over this figure. So, what it did, a complete problem is converted to some overlapping sub problems like this, okay, and thereby this reduce the dimension of the problem, or this reduce the overall problem into a set of problems which we need to solve one by one. Okay. And this sub problem 1, you can see it is independent of sub problem 2, and thereby you can start this solution of sub problem 1 first, and this solution will be transferred to this next problem in order to solve this sub problem 2, and so on, and then finally we get the complete solution. Okay. And that is what the philosophy of this overlapping sub problem. Okay. So, it starts with a problem which is independent of this all other problems, and then one by one we will keep solving the other sub problems as well. Okay. Now, here this solving about using this dynamic programming for multi objective optimization problem, here we use this weighted approach, and we convert these two objective functions into a single objective, that is C t, and with these two weights W 1 and W 2, where we use different weight combinations to get a set of solution which we require for to represent in multi objective optimization problem. Okay. And we use two approaches, one is non iterative approach, another is called iterative approach. In non iterative approach, this structure or topology of the network is first determined, then this branch conductor size is chosen afterwards. Whereas, in the iterative two step process, both are simultaneously done. So, both the determination of network structure or network topology and conductor sizes are done simultaneously. Okay. This is an example how this dynamic programming is used in distribution system planning problem. We divided all these black nodes are representing these loading points or load nodes, and this one as usual is representing the substation, and we know the substation location. Okay. And this is basically service area, this rectangle is basically service area under the substation. Okay. And as per our this requirement of dynamic programming, we divided this whole service area into number of stages, stage 1, stage 2 to stage m. Okay. Stage 1, stage 2 to stage m, and we will start with one particular stage as a process of a solution of a sub problem. So, here we will start with not stage 1, rather with stage m, because the philosophy was at the end of this network, or the loads or nodes which are located distant away from the substation, they are somewhat independent in the flow of power. So, they only carry those lines which are connecting these distant nodes, they only carry the load currents of individual nodes only, which you have seen. But in substation, near to the substation, the distribution lines are carrying the loads of all the nodes of a network, and that is what the philosophy behind consideration of the farthest nodes as the first stage to initiate this dynamic programming. So, we will start with stage m and we will solve this sub problem first. Okay. We will start with this leaf nodes or the n nodes, or the nodes which are the n nodes. Okay. And then we, after getting the solution, we provide it to the stage m plus 1, and this solution is called as sub network 1 here. So, whatever solution we get by solving this stage m, that is sub network 1, which is submitted to the next stage in order to get sub network 2, and so on. And then after solving this stage 1, we will get the final network topology. This is the flow chart of network structure or network topology optimization in order to find out the roots of individual lines or feeder branches. Here you can see, in order to go in order to understand this flow chart, one needs to go through this paper, which is published in Elsevier journal, that is IGEPS, International Journals of Energy Power and Energy System. So, you can see that we have initialized two arrays, one is alpha and beta, and this B is a matrix which is a p defined matrix, which assign that interconnectibility between two nodes. If this is 1, then it is possible to build a network branch or distribution line, otherwise 0 represents it is not possible to build a line in between this node p and q. Now, this alpha is initially null for the first stage, and that is stage m here, and beta is consisting of all the rest of the nodes. Now, slowly when we connect one node to the this sub network, we we put it to alpha and we remove it from this array beta, and that is what is done. If you go through this, you will be able to understand. Now, this is how we select this branch conductor size. Okay, that is the flow chart to select this branch conductor size. Now, if we do these two sequentially, that we first determine this conductor network structure and then we assign this conductor size, then it is called non-iterative two step approach, and if we do it together in a iterative approach, then it is called an iterative approach. So, you can get a flow chart of both the approaches over here. Okay. And this is an illustrative example how we get the solution stage by stage for 21 node system. Here this is our 21 node system, and this is what pre-existing network, as you know. So, this is the stage, the stage where we start this problem. Now, after solving this problem, we get a partial network here, which is submitted to the next stage, and then we developed another partial network, which are represented by S1 and SN1, SN2 and so on. S1, Sn basically represent sub network. So, we first determine this SN1 in this stage of optimization, then we get both SN1 and SN2 in this stage of optimization, that is the next stage, and this is submitted to the next stage, and we get this sub network which consists of SN1, SN2, SN3, and then finally, we get this sub network, and then finally, get with this full network. Okay. So, this is how you can see this network is building. So, network is building up, okay, by using the philosophy of dynamic programming. Okay. and by varying these weights into different combinations, we get different solutions, and we here are the Pareto approximation fronts or Pareto fronts that we get. That is the final non-dominated solution that we got in this dynamic programming approach. So, these are the solutions and these are the different number of weight combinations that we took in 21 node, 54 node, 100 node, and therefore, you can see in 21 node we get more number of solutions, because we have taken more number of weight combination, but for 100 nodes network we get less number of solution, because we took less number of weight combination. Okay. And this is an example for this by varying these stages. This is the sensitivity analysis with varying stages. So, if we have more number of stages, we get the computational time somewhat lower, and if we take the less number of stages, the computational time will be much higher. Okay. Similarly, this is the comparison of these two approaches. One is non-iterative approach, another is another is iterative two-step approaches. There is the comparison of computational time. Iterative approach of course takes higher number of simulation time. Okay. This is the comparison of with multi-objective evolutionary algorithm. So, here we propose this dynamic programming as well as SPATM-UPSO, and we made this comparison in view of Pareto approximation front as well as the execution type of computational time. Okay. So, which shows that this Pareto front that we got in dynamic programming is somewhat better in different systems, but computational time that the dynamic program takes to execute is much higher, specifically when this number of node of the system is getting higher. Okay. So, for 100 node system it takes 892 minutes, 892 minutes to solve. So, which is a huge amount. Okay. So, based upon that we can conclude that dynamic programming performance as well. Okay. This is the comparison of this multi-objective genetic algorithm, which I already have shown you, proposed by this author in 2006 in IEEE paper, and the result that we got for dynamic programming. So, what we get that performance of dynamic programming is even better, but and it is also simpler to implement, and but it suffers from the curse of dimensionality, means that when we have higher number of dimension in a problem, it takes a very long time to execute. Okay. So, in summary, this dynamic programming can be used as a viable alternative for solving this multi-objective optimization problem, but it suffers from this problem of curse of dimensionality. Okay. And it performance wise it provides solution which are somewhat better than the meta heuristic approaches. Okay. So, with this I will stop today, and I will continue in the next lecture.